Okay, here we are at the inclined plane problem, sort of joined with the Atwood machine with an additional layer of difficulty because in the Atwood machine you've got a pulley with two masses hanging from each string, and the system is completely vertical, so motion is only either up or down for either of the masses. Of course, now we have an inclined plane that makes it a bit more complex because now we have to consider the incline as well as the Atwood machine all into one problem. So let's get started. The first mass hanging, I'm going to call M1 because I feel like it, and the second block hanging, or the second block which is on the incline, I'm going to call M2. Now let's just jot down what they have. M1 in the problem happens to be 10 kg. M2 in the problem is given as 5 kg. So the first question is it possible to have this system be in static equilibrium? You would imagine yourself setting it up as it's drawn in the picture. And again, this is frictionless. So let me make that note here. It's a frictionless incline and pulley. There's no friction yet. We will have to tackle that soon, but not yet. So with that being said, there's no friction anywhere in the system, on the incline or in the pulley, and there's no air resistance because that's actually a form of friction as well. There's no friction, so you don't have to worry about any of that stuff. With that being said, is it possible that you could set up this entire configuration here and release it and see nothing move? There's no motion at all. That is to say that the net force would be zero. Is that possible? Is it physically possible? The answer is, well, why don't you think for a moment? The answer is yes, it is possible. It's not to say that that'll be the case here. Clearly that isn't the case because part A asks me to find the acceleration of the system, so clearly it's not. But conceptually, is it possible to have the amount of force that's pulling in this direction, which is the x component, and do recall that this is our x-axis and this is our y-axis. Is it possible that the amount of force pulling block 2 down the incline is equal to the force called weight pulling on block 1? Is that physically possible? Certainly it is. We would just have to make the angle just right. Well, I don't know what angle that would be. I'm sure certainly we could solve for it, but that's not the problem. But there could be a very specific angle, and there is a specific angle where those two forces would cancel. You let go of it, nothing moves. Perfectly equilibrium. This force over here on the right cancels with the weight pulling down on the left. Of course, that's not the case here, so let's figure it out. First, we have to recognize that the x component of the force pulling down on block 2 is going to be equal to m2 times g, you can think of that as its weight, times the sine of the angle 40 degrees. I'll just reference that as theta. I should have done this first, but I'll do it now. I have to pick a direction for the sines. So I'm going to stick with this direction being negative, because typically on an inclined plane, you call down the incline, sorry, I'm just trying to clean that up, it's a little messy. Typically you call down the incline as negative and up the incline as positive. So that for that reason, this is going to have to be listed as a minus. And now recognize this important point that if this direction is this direction here for him is minus, then the direction for this guy going up also has to be minus, which means his weight is going to have to be listed as a positive. Okay, so now we're just going to think of there's some tension in the cord as this object 2 slides down the incline. There's a cord connected to it, and that cord is still pulling in the upward direction. I'll call that T2. Okay, so I'm going to go ahead and jot that down. I'm going to erase this because, of course, very quickly I'm going to run out of space. So I'm going to go ahead and write Newton's second law net force equals ma, and I'm going to write it for block 2. So let's go. Sum of the forces on block 2 equals mass 2 times his acceleration. I can leave it as a2 for now. Now I just have to insert the forces acting on block 2 as it slides down the incline, remembering there's no air resistance, there's no friction between the block and the incline, and there's also no friction in the pulley. So all possible friction forces, which are the 3 I just listed, are all out. That being the case, there's really only 2 forces that block 2 feels. The tension pulling up, even though it's sliding down, it will slide down the ramp, the tension is still yanking on it in the inclined direction. So there's only 2 forces acting on block 2, the one I just circled and this one. So now we have to list them. I'll write T2 as a positive because it's acting up the incline, and that was my choice for my coordinate system. And now I write minus FGX. Those are the 2 forces that it feels as it slides down the incline, have to be equal to m2 times his acceleration, which I'll list as a2. Now the only thing I have to do to go further is put in the expression for FGX, which is m2g sine theta equals m2a2. I can't go any further with this. Let's just recognize that there are 2 different unknowns here. One is the tension, and one is the acceleration. On the other hand, m2 is a number. Oop, can I undo that? Is there just a back button? No, there's not just a back button. So just erase it. So let's just notice that m2 is given. So I'll check it off. G we always know to be 9.8 meters per second squared. Theta is given. m2 again is given. So the only things that are unknown are T2 and A2. So that forms one of our 2 equations that we need for our system of equations. So I'll write it down here just to keep it on the side, since I'm going to have to erase this for more space. So T2 minus M2G sine theta equals M2A. Good. All right, so let's erase this now. Because now we have to turn our attention to the other block on the other side, which is certainly not as complex because it's not on an incline, so it'll be easier to write Newton's second law for him. So let's do that. Sum of the forces on block 1 has to be equal to his mass times his acceleration. Now I just recognize that there's 2 forces. There's the tension in this direction, T, and there's his weight pulling down. So I'm going to list those, remembering that his downward, for this guy right here, his downward direction has to be positive because of the coordinate system we have chosen. So I'll write his weight first, which is Fg1 minus T, because again the tension is pulling in the upward direction. That's in what I've called the minus direction. And now I write the sum of those forces has to be equal to his mass times his acceleration. Okay, the only thing I can expand upon at this point is the expression for his weight, which is, of course, his mass times g minus t equals his mass times his acceleration. So the key idea again now is that, well, before I say the key idea, let's recognize that we know his mass, we know g, we know his mass. So there's only 2 unknowns, t and a again, as they were over here, T and A. And the key idea now is that the tension in the rope is the same everywhere. There's no difference if you tested the rope in one spot versus testing the rope in the other spot. The tension is the same everywhere. And therefore, the T over in this equation and the T over in this equation are the same. And for that reason, I can erase the 2 over here. Just call it T, since it's one value for both systems, or for both objects in the system. And as well as the fact that since their distance is staying fixed as the object goes down the incline, and actually I'm saying down the incline, and I haven't even considered whether that's actually going to be the case. I guess I don't know, now that I look at it. I don't know whether the object on the incline is going to go down the incline, or if the one on the left is going to actually provide more force and it will go up the incline. But either way, it doesn't matter which way they're going. There's one rope attached to both of them, and it's going to provide the exact same tension on force on both objects. And that recognition allows me to remove the subscripts for t under both equations, and also the accelerations for both of them are going to be the same since the distance between them stays the same. That means their speed must be increasing at the same rate, which is called acceleration, such that the distance between them stays fixed. So I'm going to erase the A1 and just call it A, just one value. So this is M2 and this is just A. So now I've got two equations, here and here. And so now I'm going to solve one of them for one of my unknowns, sub it into the other one. If I'm being asked to solve for the acceleration, then I can't just randomly choose which one to accelerate. I just can't randomly choose which variable to solve for. I have to choose wisely. If I'm being asked to solve for A, then I have to eliminate t. So to eliminate t, I have to solve this one here for t. So let's do that. T equals m1g minus m1a. Now that's going to get subbed in on this equation over here for t. So let's erase, make some room, and proceed forward with the problem. So now I'm going to just rewrite this equation over here with this expression in for t. I'm going to have to do my best to do it in some small font because I'm running out of space, so let's erase some of this too. Okay, so I'm going to write this now first in for t. I'm subbing it in, so I have m1g minus m1a, and that's now, I could put in parentheses because it's a quantity that represents the tension in the cord. And then I continue with this bit over here, minus, I hope I don't run out of space, minus m2 g sine theta equals, what's theta? Equals m2a. Good, I fit it on the board. Now, let's take a good look at it again. What am I doing? Because I often ask myself that question in the middle of a problem, get wrapped up in the math, and just try to reconnect with what is our purpose now. Our purpose is to solve for the acceleration of the system, which presents itself over here, as well as over here. So in order to solve for that thing, and also before I do, let's recognize that, why is it doing that? Let's recognize that I know M1, I know G, I know M1, I know M2, I know G, I know theta, I know M2. So I know everything in this big long equation other than the acceleration which is here and the acceleration which is here. So now we've got a math problem. We've taken our physics problem and boiled it down to a math problem, which is of course always the case because mathematics is the language of physics. Okay, so in order to solve for A, which is, oops, I did not mean that to be still the eraser. Let me put that back. In order to solve for A in A, I have to get them on the same side of the equation. That's my first goal, and then I can factor out. So let's do that. I'd have M1G. I like my red pen. Let's go back to my red. Okay, so I have M1G minus M2G sine theta. I just wrote this one down and this one down, recognizing that this guy has to come over to the right side. So that'll be equal to M2A plus M1A. Good. Now I'm going to erase all of this, make some space for myself. In fact, I'm going to erase all of this as well, just because it's not necessary to have that there anymore. Now I'm in a good position to solve for, at least to make the next step to solve for A. So I'm going to go ahead and factor it out. Red pen, please, thank you. A, factored out, will give me M1 plus M2 equals. Now you're asking yourself, well, you should be asking yourself, is there anything in this bit over here that I can factor out? Which is the same to say, is there something common between the M1G term and the M2G sine theta term? And you can think for yourself for a moment. Yes, it's G. So let's go ahead and factor that out. G, now I put in M1 minus m2 sine theta. Don't run out of room. Ooh, good job. I didn't run out of room. Okay, so there we go. And now to solve for, again, A, which is the purpose of this whole thing, all I have to do is divide over this quantity m1 plus m2, the sum of their masses. So let's do that in our final step. A equals G times m1 minus m2 sine theta, quantity closed, all divided by the sum of their masses, represented as m1 plus m2. Wonderful. We're done. This is now called deriving a formula for the acceleration of the system. Now, if we're given specific values, as we were for m1 and m2, which are 10 kilograms and 5 kilograms, and we know the angle theta is 40 degrees, which is here, then we should be able to just plug a whole bunch of numbers in right now and get a numerical answer. So let's do that. Eraser, please. Thank you very much. Here we go. I'm just going to erase all of this, which will take me a minute, so be patient. Erase, erase, erase. Nice and clean, just like my whiteboard. It's cool. Okay, nice and clean. Now, let's just continue forward and sub in our values. A equals... Now, when you see G, this is a key moment. You want to put in the magnitude of G plus 9.8, not minus 9.8. We already took care of the directions when we set up the problem, when we chose our coordinate system, and we gave some direction plus and some direction minus. That already had taken care of the directionality of G. So you do not want to put in negative 9.8 here. So let's stick with that. Let me erase. I'm going to go ahead and put in 9.8, and maybe I should be a little more careful because I'm going to run out of room. So let me start over here. I'll write A, get rid of that red line that doesn't belong there. A equals 9.8 times, what's M1? 10, minus M2, which is 5, sine of the angle, which is 40, close parentheses, divide by the sum of their masses, which is 10 plus 5. Now, of course, I need a calculator for this, and naturally I do not think ahead and grab one, so I'm grabbing one as we speak. Being a physics teacher, I never have a calculator too far away. So I have it. Here we go. Let's see. I'll make sure that I am in degree mode since I have sine 40 in my equation. Mode, let's check. Yep. Good student, conscientious student will always do that. Now I continue forward. So let's do it out. I'm going to do 10 minus, well, let's just do this, 5 sine 40. That's 5. That's just how I tend to work backwards. If you'd like to do it a different way on the calculator, that's fine. 5 sine 40, I got that as a number. Now I do 10 minus that number. I multiply it by 9.8. Now I divide by 15. Enter. So I get 4, there we go. 4.43 meters per second squared. So this is where we have to think about the sign, because the sign of this will tell me which direction the whole system accelerates. So let's reconnect with the directions that we chose way back in the beginning, and I'm going to erase this just to make some space. Remember that I had originally called this the negative direction, and upward is the positive direction. Since my answer came out as positive, it means it's actually going to move in the positive direction, which is up. So it means that the weight of object 1 over here, straight down, is greater than trying to get the eraser. It means that his weight is greater than this guy's component, FGX, pulling down. It means there's more force pulling in this direction than there is pulling down, which means, of course, the man on